Right, so the next section is regenerative power cycles, right? Regenerative vapor power cycles. So another commonly used method for increasing the thermal efficiency of vapor power plant is regenerative feed water heating. Right? Now, what does this mean is, now if you remember the boiler action, what the boiler do is once the pump feed water pumps to the higher pressure. So after that, boiler take place from here all the way up to here, right? So you have subcooled liquid here at this point, right? Subcooled liquid, then heating up to saturated level, then again after superheated level. So this is the boiler action, right? So what the regenerative power plant do is, instead of giving all the heating to the boiler, what it do is basically it heat up the feed water. Now in this region you have subcooled water, right? Before entering to the boiler, we use feed water heaters, intermediate device we call feed water heaters. We use feed water heaters to heat the things up and then feed into the main boiler, right? So how we heat the thing is using the steam generated from the boiler itself, right? So now when we talk about feed water heaters, there are two types of feed water heaters. We have open feed water heaters and we have closed feed water heaters. Now what happens in open feed water heater is we going to mix the thing. Now how the heating happens, now let's we consider this diagram. So you have a turbine, right? So we draw a steam line in somewhere in the middle of the turbine. Now this not the two set of turbine as in the reheat. This is not two set of turbine, high pressure or turbine. No, this is the actually one set of turbine, right? What we going to do is we draw some steam line somewhere in the middle of the turbine and get the steam line mix with the feed water. Now this is the condenser, and after condenser you have 100% liquid, and 100% liquid is pumped back, increasing the pressure using the pump. Then so you have subcooled liquid in here, right? Okay, so subcooled liquid, and that liquid is mixed with the steam line. And mixed with steam line we call open feed water heaters, where the steam and the subcooled water mixed together such a way that it will increase the temperature of the feed water, right? So if we then again it's pumped back. Right? Now in this setup you have two set of pumps, right? And we have a steam line drawn from somewhere in the middle of the turbine, right? So if you look on the TS diagram for this one, now normally it should be goes like this, right? So the boiler take place from A up to 1, right? Then 1 to 3 is the turbine action, right? Then we are drawing some of the steam line in the intermediate section, let's say number 2, and then mix that with the feed water heaters. Now so this 4 to 5 is the pump 1, 4 to 5 is the pump 1, and 6 to 7 is the pump 2, number 2, right? Pump 2, right? Now what happened in here, the energy that drawn from point 2, it's rejecting, that means given their heat such a way it comes from 2 to 6, right? From superheated, then saturated, 100% liquid to all the way back to the 100%. So 100% gas here, then to 100% liquid. So while it comes from 2 to 6, it gives the heat such a way that 5 to 6 will heat up, right? So the 5 to 6 the energy gain, the heat gain from 5 to 6 equal to energy rejected or energy absorbed by the 2 to 6 steam. So you have the steam here, then steam become saturated gas, again then saturated liquid there, and you have in here you have feed water subcooled liquid, then it becomes saturated liquid at number 6. So heat rejection from 2 to 6 equal to heat absorption from 5 to 6, right? Such a way then after it will pump the things back using the pump too, right? So this will again basically increase the efficiency of the system, right? So this is the open feed water heaters. Then you have the same, which is closed feed water heaters. Now what is happening with closed feed water is they are not going to mix the thing, right? So steam is circulated back. Now this is the steam that drawn from the in the intermediate section from the turbine. So that is drawn here, and you have a heat exchanger here. Now instead of mixing the thing, now this is mixing the things, but this is not mixing, right? So you have a heat exchanger here where the steam is passed to the heat exchanger and again feed back to the condenser, right? So this is a separate path, and the main path here is flowing separately to the boiler, right? So there's a heat transfer in here, so such a way that drawn steam from the point 2 reject heat in this way up to 2 to 7, right? And that heat is absorbed by 5 to 6, right? This is 5 to 6 heat absorbed to the 5 to 6 equal to heat rejection or heat heat that dissipate from the 2 to 7, right? Again then it's you have the trap, again a regulator here to match the pressure, then it will add somewhere in the middle of the condenser to the condenser, right? So this is the TS diagram for closed feed water heaters, right? Then in normal configuration, if you look on typical steam power plant, you will find multiple feed water heaters. That means you have several feed water heaters. It can be either open or closed, whatever it is. You have several feed water heaters. So the thermal efficiency of the regenerative cycle can be increased by incorporating several feed water heaters at suitably chosen pressures, right? The number of feed water heaters used in is based on the economic consideration, since incremental increase in thermal efficiency achieved with each additional heater must justify the added capital cost like heaters, pumps and piping. Like that's what it means. If you add a feed water heater, it will surely increase the efficiency, but you have to justify that one. You know, adding a feed water heater is initially a high cost, because you know at the heat exchangers, pipelines and everything should be there, and that increase in the capital should be justified by the thermal efficiency gain that by adding that feed water heater, right? So normally power plant designers use computer programs to simulate the thermodynamic cycles, and also decide they use computer programs or simulation to decide what kind of feed waters are needed and how many of them are needed in a particular plant, right? So this is one of the examples. Now in this diagram you can see there are 3 closed feed water heaters, one here and another there, and you have open feed water here, right? So so you can see there are steam is extracted from different point, right? 2, 3, 6 and 7. Likewise the steam is extracted, and again they are directed to open and close feed water heaters for heating feed water, right? So if you look on the main part, now this one has a two-stage turbine. You have a high pressure turbine, then you have the reheat, again the low pressure turbine section, and each of these, so basically you have two sections, high pressure and low pressure. Then in the intermediate point, it get drawn back some of the steam for reheating, so for feed water heating, right? So if you look on this diagram, you have the main part going here, then after that to the high pressure turbine, then reheat it again, the low pressure turbine, and again back to the condenser, right? Then the pump 1 goes to first closed feed water heater, then again open feed water heater, then pumping again back, again two set of closed feed water heaters, right? So this is how normally a system look like, right? But that even get complex. Now I will show you the one of the let me see. So now this one, so this is the diagram for Norachole power plant, right? So if you you know, we have three set of identical 300 megawatt of steam steam turbine. So this is one set of turbine, right? So now by looking at this, you may feel that this is like very complex, but if you break down things a little bit, you will be able to understand. Now you have the high pressure turbine here, right? Now this is the HP, means high pressure turbine. Now, and again it has intermediate pressure turbine, right? Now this has three section: high pressure, intermediate pressure, and low pressure turbine, right? And if you look on this, these are all the feed water heaters, right? So you have closed feed water heater 1, 2, 3, 4, 5, 6, 7, and 8. So there are 8 closed feed water heaters, and again there's a one open feed water heater, right? So this is the actual diagram of the Norachole power plant, right? So so it is bit of complex, but by looking at this you will understand what that means. So this is the real situation in the real steam power plant, right? And you can see there are pumps here, and a pump there, another pump here, again pump here, likewise, right? So if you look on the path, so steam enters in the high pressure turbine, right? The high pressure turbine, then again go back to the boiler, then from the boiler it comes back to the intermediate pressure turbine, right? And some of the seams are drawn for, now you can drawn for feed water heating. Now here you have the, from here you have the open feed water heater, again and the line is drawn for closed feed water heater, likewise we have, can see there. And after that it goes back to the, now this one goes back again back to the boiler, and from the boiler it's come back to the low pressure turbine, right? Then you can see there another path drawn for feed water heating, right? Then again all the main line goes back to the condenser, they can pump it back, then goes through the feed water heaters, right? Then open feed water heater here, and then pump it back, then again to close feed water heaters, and then back to the boiler, right? So this is how the diagrams look like. So this is the actual situation, right? Okay, let's work on the example. So this example is about open feed water heater. So consider a regenerative vapor power cycle with one open feed water heater. So we have one open feed water heater. Stream enters the turbine at 8 megapascal, 500 Celsius, and expand to 0.8 megapascal, where some of the steam is extracted and diverted to the open feed water heater operating at 0.8 megapascal. The remaining steam expands to the second stage turbine to the condenser pressure of 0.01 megapascal. Saturated liquid exits the open feed water heater. Now this part is important, right? So the saturated liquid exits from the feed water heater at 0.8 megapascal, right? Each pump operate isentropically. So why each pump means, because if you remember the open feed water heater, you should have two pumps, right? Because one pump need to be pressure from 0.01 condenser pressure to 0.8 pressure, right? The second pump pressurize from 0.8 to 8 megapascal, right? There should be two pumps, right? That's why each pumps are there. That means there are two pumps, each pump operate isentropically. If the net power output of the cycle is 100 megawatt, determine A, the thermal efficiency, and the B, the mass flow rate of the steam entering the first turbine state in kilogram per second, right? So I want you to try this one on your own first, right? It doesn't matter you not be able to complete whole the thing, but at least to some extent, but right, at least try to figure out the schematic diagram as well as the TS diagram for this particular problem, right? Later on you can work with me with the video and see how it's done, right? Okay, so let's we work on how we can do this kind of question, right? So if you remember our Rankine cycle, so there are four components: boiler, we have the boiler, turbine, condenser, and the pump, right? So what is difference is in here, right? So you have a feed water heater here, and instead of one we have two pumps, right? Okay, now let's see figure it out what's happened. So boiler is the where the Q is in, right? Okay, so Q in here, and the turbine you can get the work output, right? In here you get the W out. Okay, what's happening, right? Okay, never mind. So the condenser, you get the heat out, right? You get the heat out, and then pump, you have the W in, and we have open feed water heater, right? So let's we map this diagram with our TS diagram. So the boiler, boiler start from number 7, right? Number 7 here, and heating up all the way to superheated level, right? So basically you have TS diagram and you have the three pressure lines, right? So you have 8 megapascal line here, and the 0.81 here, and the 0.01. so this is the condenser pressure. So this is the intermediate pressure, right? Where the feed water heater is operating, and then you have the turbine pressure or the boiler pressure here, right? So then so boiler start from number 7 to 1 is the boiler action. Use heating up the until it reach to this point, superheated level, right? Then turbine action. In the turbine, pressure drops, right? And this isentropic expansion, therefore no entropy change, right? 1 all the way to 3, right? 1 goes 3, right? Is the turbine action. Then we have the 3 to 4 is condenser action. That means we have Q out, right? Q out, right? Then we have pump action. So this is the pump 1 action, right? This is the pump 1, right? That is the 4 to 5 pumping from 0.01 to 0.8 megapascal, right? Pump action. Then we have a 5 to 6 is the feed water heat action from 5 to 6. Then 6 to 7 again we have pump action, pumping pumps 0.8 to 8 megapascal, right? So this is pump. So 4 to 5 pump 1, 6 to 7 pump 2, right? So then what about the heat exchanging process in open feed water heater? So you have a drawn here, a steam drawn here somewhere in intermediate line, which is 0.8 megapascal, you draw it from here, feed it to the heat exchanger. So whatever the steam coming from here, that means point 2 dissipate heat. Now it's point 2 dissipating heat up to 6. That means this heat, whatever the heat given by this process, will be absorbed by 5 to 6, right? Okay. And also we have another concern here, right? Because you can see now, let's say you input 1 kilogram of, right, 1 kilogram here, right, 1 kilogram of steam, right? Then from that 1 kilogram, some portion will be goes here from 2 to 6, and some portion will be going from here. Therefore we can say that fraction or that portion is y, right? So how much fraction that it extracted from here, we can indicate that one as the y, right? Okay, y, right? So that is what is indicate here, y. So if you get 1 from here, then y goes out, then what is the remaining here? 1 minus y, right? That is why it is indicating here, that way, right? So the first question is to find out the thermal efficiency of the cycle, right? So we can start from there, right? So the neta we can write W out over Q in, right? Then W out. So let me try to figure it out, what is Q in and W out. So the Q in, so this is the Q in, 7 to 1. The boil action is the Q in, where we adding the heat. Therefore Q in is H1 minus H7, H1 minus H7, right? Then W out, right? So W out is somewhat different. So if you remember the last time, normal Rankine cycle as well as the reheat Rankine cycle, we get W out as H1 minus H3, right? Whatever the enthalpy in here minus whatever the enthalpy in here, right? But in here we have a problem, because you get you are running 1 kilogram of here, but in here you get 1 minus y, because some fraction, some amount of steam is drawn back, extracted for feed water heating, right? Therefore we straight away we can't say W out is equal to H1 minus H3. Instead what we can say, W out is equal to H1 minus H2, because you get the 1 kilogram here, right? You always get the 1 kilogram here, then it divided y and 1 minus y, right? Then we can say H1 minus H2 plus 1 minus y times H2 minus H3. So that is our W out, right? Okay, I hope you understand what I'm saying, right? So then that is the W out. So let me figure it out, that one. Then let me see, to find the neta we have to find H1, H2, right? We have to find H1, H2, H3, H4. We don't need H4, right? Okay. H1, H2, H3 and H7, right? And also we need Y, right? Let's see Y. So let's we first formulate equation for Y, right? So whatever the heat dissipate from 2 to 6, that means when the steam cools down from 2 to 6, that heat will be absorbed by 5 to 6, right? So you get y amount of mass here, then 1 minus y amount of mass from here, right? Therefore we can write, considering the energy balance for the open feed water heater, the heat from here y times H2 minus H6, that means this heat y times H2 minus H6, that is the heat from here, right, should be equal to 1 minus y times H6 minus H5, right, 1 minus y times H6 minus, right. So if we know all the H values, then we can find the y here, right. So this is our way to approach for finding the neta. So that means we had to find H1, H2, H3, right. H4 we don't need, right. H5, H6 and H7, right. Now instead of H4 we had to find all the H values, right. But of course to find the H5, right, we need H4 as well, right, otherwise we can't find the H5, right? Because this is a pumping operation. If you remember, the pumping is P delta V, right, sorry, V delta P, V delta P, right, okay. So that is equal, V delta P equal to H4, H5 minus H4, right. To find H5 we need H4 also, therefore that means we need to figure it out all the H values, right, H1, 2, 3 up to 7, right, to find the neta. Therefore let we first figure it out, that one, all the H values, right, all the enthalpy values, then we can come back to point A and calculate for the neta, right. So let we start from here, the H1 from 1, 2, 3 likewise. So point number 1 is in superheated region, we know that, therefore we can straight away look for the tables, figure it out what is the H value, right. So let me look on the tables. So we are interested in superheated tables, right, superheated water tables, right. So the superheated water tables are in A6, right. So right, so I'm interested in 8 megapascal and right, so this is the one we are interested in, right. So this column is what we are interested in. Pressure is 8 and the temperature is 500, right. Therefore we can extract the H value, H equal to 3399.5 and S value, entropy value 6.7266, right. So that is what is again in here, right. So from there we can say H1 equal to 3395.5 and also S1 should be equal to S2 should be equal to S3, that's equal to 6.7266. Why is this? Because you can see this is a isentropic expansion, therefore S1 should be equal to S2 should be equal to S3. So this is straight away, right, vertical line, right? All S value should be equal to on that one, right, 1, 2, 3, right. So then the next one is to finding, so we know the H1, right, next thing is to find the H2. So how to approach that one is using the entropy value, but that means we know the S value here, right, that means entropy value, then we can refer that entropy value in the table to figure out what is the H value, enthalpy values, right. So S2 equal to 6.7266, right, and of course we know this point should be in superheated region and the pressure is 0.8 megapascals. So therefore we can refer the table, superheated table, right, superheated table 0.8. So we have the 0.8, so here we have 0.8 megapascal, right. Then the S value, our interesting value is 6.7266, right. So we have to find 6.7266 6.7 is in between this one. We have 6.66 as well as 6.81, right? So what I'm going to extract these two values as well as the enthalpy values, right? Then that is what is indicating here, right? So we have 6.616, the upper bound, and the lower bound 6.8177. so our interesting value should be in between, and also we have extracted the H values, enthalpy values, right? Okay, so 6.6616 there, right? That is the upper value and this is the lower value, as well as these two enthalpy values, right? Then we can find the X fraction for this one. So fraction X we can write like this: 6.7266 minus 6.6616 divided by that means this distance divided by the whole distance, right? Then it becomes 0.4164. Once you have figured out the X value, then you can find the H2 values according to this equation, right? H2 equals to this value plus the fraction times this difference, this length, right? That means 2839.8 minus 2768.3. so if you calculate that one, then the H2 become 2798.07, right? So we have figured out the H2 value as well, enthalpy at point 2. Then let's we move on to point 3, right? So far we have figured out 1, 2, now we are in point 3. Now point 3 can be anywhere, either it can be in the mixture region or it can be in superheated as well, right? Therefore first thing is we have to compare the S3 value, the entropy value, S3 value with these saturated values, saturated value here and saturated value here. For that let me refer the saturated tables, right? From saturated tables, okay, from saturated table at 10 kilopascal. Why is 10? Because the pressure is 0.01, that means 10 kilopascal, right? Then if we refer that one, so we are interested in 10 kilopascal. So this is 10 kilopascal saturated pressure table, and this is the 10 kilopascal line. You can see the SG is 8.14 and SF with this 0.64. so our interesting point is, that means the S value is, you can see 6.72, right? So surely 6.72 is in between this one, right? So this is the lower bound, this is the upper bound, right? Therefore we can say it is in the mixture region, saturated region. Then therefore we can write this equation, right? This way we can extract these two values, 0.6492 and 8.1488 from the saturated tables, right? Let me go back and see. So this is the lower bound, 0.6492 as well as the 8.1488. so we can extract these two values, right? So these are that two value, lower bound and upper bound, and our S value should be 6.7266. therefore we can calculate for the X likewise. So then X becomes 0.81036, and also we can extract the H value from the table. So H value, so this is the HF value, this value, and this is the HG value. Then so we can extract these two values and then find the H3, calculate for the H3. So once we have figured out the X here, then we can apply that one to find the H3 values. So this is the equation. Then we can figure it out. H3 equals 2130.264 likewise. Okay. So up to now 1, 2, 3 is okay. Then from the table, same way we can figure it out. H4 value as 191.81, the same value in here. that we extracted from there, it should be H4, right? Then H4 is also okay. So the next thing is H5. So let me go back and see. So H5, so this is the pump action. If you remember, the pump action is equal to V delta P. Therefore we can say V delta P equals H5 minus H4. Okay. So the pump action is H5 minus H4 should be equal to V delta P. So VE is the volume that we can extract that from the saturated tables. Okay, let me go back. So we are interested in 10 kilopascal, and the V is 0.001010. Saturated liquid volume, right? That means specific volume of saturated liquid, right? So we can extract that value. So this is the V, and delta P. Delta P is 800 minus 10. Why? Because pump is pumping up to 800 kilopascal. That means 0.8 megapascal minus 10 is our delta P. Then again we can say H5 equal to this times plus H4 value. So this is the H4 value, delta V delta P plus H4 equal to H5. Then you can figure it out, this one like that, 192.608. So H5 is known. Therefore then we can move on to H6, right? Let me go and so H6 is exactly on the saturated line, right? You can I highlighted that. If you remember, the saturated liquid exit the open pit water heater at 0.8 megapascal, right? That means, so this what is exit from here is saturated liquid. That means this point is exactly on the saturated line. Therefore we can write we can refer 0.8 megapascal line and refer to saturated tables to figure it out this point, right? Then if we go back, so our pressure is 800 kilopascal, right? 800 kilopascal, and our HF value is 720.87. So this is our H6 value, right? So that is what I have extracted from that I have written in here, right? There it is. Okay, here it is. H6 equal to 720.87 kilojoule per kilogram, right? Okay, that's okay. Only one to go. This is that is H7. So what we have in H7 is again a pump action, right? So this one also pump action. Therefore we can write H7 minus H6 equal to V delta P again, right? So delta P is 8000 minus 800, right? 8000 kilopascal minus 800 kilopascal, right? Then we can figure it out the V value also in here using the table. So 800 V is 0.001115. So this is the V value, V delta P. Then we can apply for that one. Then S7 minus H6 equal to V delta P. So this V delta P, this part is the V delta P plus H6. So this H6, so we have figured out H6, therefore equal to H7. So therefore H7 becomes 728.898. So far we have figured out all the H values. So the next thing is find the Y, because we need Y. Y means how much the fraction, what is the fraction that drawn from this point 2 is the Y. If you remember, we have construct the equation for Y, which is this one, right? So we know H2, H6, H5, everything we know, only the unknown is the Y. So if we can substitute for this equation, we can find the Y value. So that is what I have done in here, right? So that is the value. Then we can figure it out. Y equal to 0.2547. That means 25.47 percentage of steam will be extracted for heat water heating, right? That means if you pump 100 that's 1 kilogram of steam, then 250 around 250 of 50 gram of steam will be extracted for feed water heating. Then again 750, roughly 750 gram of steam will be passed to the second set of turbine. That's what this means. Okay. Then straight away we can write neta equals to W out minus Q in. If you remember, we have construct the equation for W out, right? So all the things are known, therefore you can simply, and Q in also H1 minus H7, all the things are known, therefore you can simply substitute this one and calculate for the neta value. So neta becomes 0.4116. And also W out, so I have calculated the W out equal to 1099.14 kilojoule per kilogram. So that is the W out, right? So that is the part A. And the part B asks what is the mass flow rate of steam entering the first turbine stage, right? So therefore we can calculate something like this. So the power output is 100 megawatt. So that 100 megawatt, let me assume the m dot is the mass flow rate. If so, mass flow rate times the W out, right? W out, so what W out in here is the kilojoule per kilogram, right? Per kilogram. Therefore we can say W out time m dot should equal to 100 megawatt. Therefore we can say m dot equal to 100 multiplied by 1000. That is, we can that means we need to convert into kilowatt, right? Then divide by the work output, W output. So this is the W out. So the W out is 1099.14. Then if you substitute that value, you get 90.98 kilograms per second. That means per second there will be 90.98 kilograms pass into the first set of turbine, right? So that's how we can work on this equation. And also so this question is about open feed water heater, right? Okay. What about the closed feed water heater? If you given the question about closed feed water heater, now if you remember, the only thing that differs here is how we can figure it out, this Y value, right? So in this case, so this open feed water heater, so if what happened here, the Y amount of steam is drawn in here, therefore you get here is 1 minus Y, right? If you extract Y, here you have 1 minus Y, therefore the energy balance become Y times H2 minus H6 should be equal to 1 minus Y times H5 minus H6. You remember our equation, right? That is okay. This equation, right? So that is the energy balance. So this energy balance is for the open feed water heater. If you are given a closed system, right? Closed feed water heater, then you are extracting Y times, right? You are extracting Y, and but then this is 1 minus Y, but that Y amount is directed back to the condenser here, right? Therefore what is you are getting from here is again Y. So what you are getting from here is Y again, right? Because you have Y, sorry, this is 1 again, right? So you are pumping 1, you are extracting Y here, then what you have in here is 1 minus Y, and you are again pumping Y here, right? Then you get Y plus 1 minus Y, then these two cancel out, you get 1 here. What you are getting is 1. So the energy balance for this one become something like this. So this is the Y amount, so right, Y times H2 minus H7, so that is the heat dissipate from when the steam travels from 2 to 7, right? So the heat supplied by the extractor steam is Y times H2 minus H7 should equal to, right? So this energy should be equal to 5 to 6, right? So this heating is achieved, 5 to 6 heating is achieved from this energy, right? Therefore we can say this one should be equal to, so what we are getting from here is again Y, because we are getting Y here and in here 1 minus Y. So this is the point inside the condenser. Then what you getting in here is again Y plus 1 minus Y. That become 1. Therefore 1 here. That means that should be equal to, this should be equal to H6 minus H5. Right. So that is the energy balance for open feed water heaters. Sorry, closed feed water heaters. Right. So if you are given a question, so this is the only part that differs from the open feed water heater. How we can construct the energy balance for the feed water heater. Right. So with that we can close this session. But before that, so the next session, I want to tell something about the next session. So the next session is on refrigerators, right? Refrigerators at heat pumps. And of course, as I tell you before, this module is the extension of what you have learned in the second year engineering thermodynamics. So this applied thermodynamics is a extension from engineering thermodynamics. Therefore you have some clash, right? I mean, you have to you should have the knowledge about the previous case, right? Therefore the next session is on refrigerators and air conditioners. And of course I have done that section in second year, right? If you remember the refrigeration cycle, so that knowledge should be refreshed, right? Therefore the next lecture will be on refrigerators and heat engines, basically the reverse Carnot cycle, right? Then later on we will discuss about absorption cycle, right? So the absorption cycle I haven't discussed on the second year. It comes under this one, but you need to have the knowledge on refrigeration cycles, right? Therefore the next session I will be posting the link for the refrigeration cycle, but of course that one is the same thing I have done in the second year, right? So I want you to refer that one as well, refresh your memory, right? Then we can discuss on the next thing, absorption cycle, right? Okay.